Hello everyone, Mr. Minnick's my name, math is my game, and today I'm not joined by any class. I'm recording this lesson for geometry without an audience of zero. So anyway, I'll try my very bestest to make this informative, educational, I don't know about entertaining wise, but it will be educational. Um, so chapter 4, we're nearing the end of it. Chapter 4, section 5 deals with some special kinds of triangles, isosceles and equilateral. Isosceles and equilateral. So the essential understanding box kind of does a good job of explaining things. There's a few things on your note-taking packet for my class that's watching this back that you'll have to fill in. And it's basically everything that's highlighted. So isosceles triangles are common in the real world. You and I can frequently see them in structures, such as buildings, bridges, also in art and in design. So the congruent sides of an isosceles triangle are called the legs. So that's something you'll have to fill in, the legs. So they're talking about this side here and this side here. The names given to those are the legs. When we go on to study right triangles in a future chapter, and right triangle trigonometry, we'll be talking about legs also. So make sure you're familiar with that word. It's just the sides of a triangle. Okay. In this case, it's the sides that aren't on the bottom of it. So the third side is called the base, B-A-S-E, the base. So the third side is called the base. Now, interestingly enough, if that triangle happened to be oriented in a different way, I could trace that thing if I wanted to. Maybe I'll use this purple crayon here and I trace that thing. Okay, if I orient that triangle a different way, maybe I spin it. If I spin it, the base is still, it's not necessarily at the bottom. It's just not the legs. It's kind of hard to explain without a real example, but this is an example, but here's a leg, here's the base still, okay? So the base usually appears at the bottom, but doesn't have to, is all I'm trying to say. So the congruent sides are the legs, the third side is the base, and the two congruent legs form what's known as the vertex angle, And the other two angles are called the base angles. So basically all those blanks in that drawing, just be familiar with the various parts. Since we're familiarizing ourselves with these terms, you could probably guess, right, that we're going to be saying something about these parts. So by definition, since we're dealing with an isosceles triangle, you'll notice that the legs are congruent. Okay. All right, so hopefully everybody's had a chance to fill those blanks in and make sense of that. So we've got a couple of theorems here, and they're virtually the same, just one goes one direction, the other goes the other direction. And yeah, I did say one direction, I'm sorry. Theorem 4.3 says if two sides of a triangle are congruent, then the angles opposite those sides are congruent. If two sides of a triangle are congruent, and usually that implies it's an isosceles triangle, then the sides opposite those angles, the angles opposite those sides are congruent. So what they're saying here is that the base angles of an isosceles triangle are congruent. Okay, so in your notes you're going to have to fill in this part that I'm about to draw a box around. If AC is congruent to BC, then angle A is congruent to angle B. So theorem 4.3 says if we have two sides of a triangle, so if we have an isosceles triangle, then the implication is that the base angles, and they're saying the angle opposite those sides. So if we look at side AC, the angle opposite side AC is this angle B over here. And if we look at BC, the angle opposite BC is angle A. So basically this is just saying that the base angles of an isosceles triangle are congruent. If you have an isosceles triangle, then the base angles are congruent. It's kind of a summary of what that theorem says. But the theorem actually says if you have two triangles and the sides, two sides are congruent, then the sides opposite those are congruent. So, all right. Theorem 4.4. Theorem 4.4 is the converse of that. It goes the other direction. It switches the hypothesis with the conclusion. So here we're supposing that we have two angles of a triangle that are congruent. Okay. So here we're saying, okay, we got angle A is congruent to angle B. And so because angle A is congruent to angle B, the sides opposite those angles are congruent. So the side opposite angle A, is this side BC. This side BC. And the side opposite angle B is side AC. Okay. So again, in your notes, you're going to have to fill in if angle A is congruent to angle B, then AC is congruent to BC. So the one of them is, one kind of goes the one direction. One says if you have sides congruent, then the base angles are congruent. The other one says if the base angles are congruent, then the sides opposite those are congruent. Or the legs of the isosceles triangle. Or it is an isosceles triangle. All right, so they kind of give this another name. They call it the isosceles triangle theorem and its converse. Okay, so we could call it theorem 4.3 and 4.4, or if you want to call it the isosceles triangle theorem, maybe you want to call it the ITT. And then the other one is the converse to it, so maybe you could call it the CITT. Anyway, let's see what happens here. Problem number 1. They're asking us is AB congruent to CB? Congruent to CB. So we want to know, are those legs, are those sides congruent? So when we want to answer that question based on what we've just witnessed, we're going to have to look at these base angles here. Are those base angles congruent? They sure are. So we could say since angle A is congruent to angle C, yes. And the reason for that is because of either the ITT or the CITT. So we're given that the angles are congruent. So let's see. If the angles are congruent, then the sides are. So that's theorem 4.4 is our reason for this. Okay. Our reason for this is because of theorem 4.4 or because of the CITT. Okay, so our reason is theorem 4.4. Or if you want to call it the CITT. The kind of looks like CI pi, the way I made those letters. All right, part B. Is angle A congruent to angle DEA? So part B is asking us, is angle A, better change colors, is angle A, is this angle down here congruent to angle DEA? Let's see, DEA, the E is the vertex, DEA, so they're talking about those angles. Are those angles congruent? Well, to answer that question, we would need to look somewhere. You know what they say, sometimes you just got to look at it. Would you just look at this? Would you just look at this? Oh, would you look at it? Would you look at that? Look at those hash marks. Because of those hash marks, again, we could say since AD is congruent to ED, yes, those angles are congruent. How do we know that? Well, let's go back. Let's take a look at those two theorems. We've got the sides congruent, so because the sides are congruent, the angles are, so that's going to be the ITT, or theorem 4.3. So this is theorem 4.3 or the ITT. Okay, so the reason here is theorem 4.3 or the ITT. Okay. Cool beans. This seems pretty easy. Wonder if they're going to get any more difficult than this. The guiding is WVS. Is WVS. So WVS, they're talking about this base angle down here, that's WVS. Is that congruent to angle S? Angle S. Well, if we look, we've got this side congruent to this side. So since the sides are congruent, the angles are congruent. So what's that going to be? Let's go back. If the sides are congruent, the angles are congruent, that's going to be theorem 4.3, right? Cool beans. So part A is yes. Theorem 4.3, the ITT. Part B says, can you conclude that RUV is isosceles? Can you conclude that RUV is isosceles? So let me erase all this other stuff and take a good look at it. Can we conclude that triangle RUV is isosceles? So to know that it's isosceles, we need to know that two sides are congruent. To know that two sides are congruent, we would need to know that the base angles are congruent. And do we know that? Is angle R congruent to angle RVU? Can we tell that those angles are congruent? Or do we know if RU is congruent to VU? Do we know either of those two things? We don't. So on this part B, the answer is no. We would need to know that angle RVU and angle R are congruent, and we don't. Or we would need to know that RU and VU are congruent, and we don't. So the answer to part B is no, because of that and that are not known, because we don't know those things. Okay. All right. So I hope everybody's having a terrific Tuesday. Well, wait a minute. It's Wednesday. I hope everybody's having the best Wednesday they've ever had. I'm not going to speculate as to whether or not we're going to get another snow day because, well, the last time I was wrong. And I'll eat crow on that. I will admit I was wrong. Really thought we were going to have a snow day, but, well, whatever. So up next then, we're looking at this isosceles triangles. They have a certain type of symmetry about them, about a line through the vertex. The theorems in this lesson tell us that there is symmetry going on, which we'll study more in chapter 9. So let's look at theorem 4.5. If a line bisects the vertex of an isosceles triangle, then the line is also the perpendicular bisector of the base. If a line bisects the vertex of an isosceles triangle, then the line is also the perpendicular bisector of the base. Read that one more time. If a line bisects the vertex angle, so of an isosceles triangle, then the line is also the perpendicular of the base. So perpendicular bisector of the base. So in your notes, you're probably going to have to fill in these two things. So if AC and BC are congruent, so that means that we have an isosceles triangle. And then they're saying, okay, also we need to know that angle ACD and angle BCD are the same. Okay, so because of that statement, because of this statement, that's kind of telling us that CD is the bisector. Okay. So then what can we conclude? We can conclude that CD is perpendicular to AB. And we know what that means because CD and AB are perpendicular. There's a right angle formed here and a right angle formed here. And we can also safely conclude that AD and BD are congruent, or that these legs here are congruent. That's pretty handy. I have a feeling we're going to be able to use this to prove some triangles congruent. It'd be kind of cool. I think I kind of gave you a preview of this in one of the examples from one of the earlier lessons this chapter. So hopefully everybody's had a chance to jot those things down, and we'll take a look at our next item up for bids. All right, so problem 2 says, what's the value of x? The problem with this, I see, is that this 54, it's kind of unclear where it's at. It's kind of just floating around in space. Where's that 54 even at? Is the 54 here? Well, probably not. It's kind of hard to tell. But they are telling us that these angles are congruent and that these sides are congruent. So we know then that BD bisects angle ABC. So we know then that BD is perpendicular to AC. So we know that these are right angles. So that kind of tells us where the 54 belongs. So 54 is the measure of angle A. Okay. So if there's a 54 here and these are an isosceles triangle, we would know that there's also a 54 down here. And if you recall the triangle sum theorem, we would know that the measure of angle, x, I guess, x degrees plus this right angle plus 90 plus the 54, that all of those would have to add up to 180. So if we get rid of that, we would know that x then would be whatever 90 minus 54 is. So that's going to be 36 degrees. So x is 36 or 36 degrees. Cool beans, that one wasn't bad. Got it says, suppose that 54 is not a 54. Suppose that 54 is not a 54. Suppose that we're working with a 27 instead. Well, we would just subtract 27 from 90 instead. So in that case, x would be 90 minus 27, or 63. I think it's kind of confusing how they made those numbers palindromes of one another, but kind of neat. Palindromic numbers. Hopefully you know what a palindrome is. Mom is a palindrome. Probably the one of the most impressive ones is race car is a palindrome. The number 3003 is a palindrome. So, all right. So maybe I should tell you about the talking sheepdog. There was a sheepdog that could talk, and the talking sheepdog gets all the sheep in the pen and tells his master, his farmer, all 40 accounted for. And the farmer says, but I only have 36 sheep. And the dog says, I know. I rounded them up. All right. That was really bad. Corollary is a theorem that can be proved easily using another theorem. Since a corollary is a theorem, you can use it as a reason in a proof. So more stuff to memorize, more stuff to refer back to. Corollary to theorem 4.3. So now we're moving on from isosceles to equilaterals. If a triangle is equilateral, then the triangle is equiangular. So theorem 4.3 in your notes, you're going to have to fill in if xy, segment xy, is congruent to segment yz, which is congruent to segment zx. If that's the case, if xy is congruent to yz is congruent to zx, then angle x is congruent to angle y is congruent to angle z. So it's basically kind of like it builds on the earlier theorem. The earlier theorem was talking about isosceles triangles. And this one just extends that idea to equilateral triangles. In the proof of that, I would imagine at some point would probably involve CPCTC. So anyway, now the next thing we're looking at is the corollary to theorem 4.4, which kind of goes the other way. So this is assuming then that the angles are all the same. If angle x is congruent to angle y is congruent to angle z, then all the sides are the same. So if we have three congruent angles in a triangle, then all three sides are congruent. So the one kind of says if we have an equilateral triangle, then it's equiangular. The other says if we have an equiangular triangle, then it's equilateral. Good. Good. All right. Moving right along then. Problem 3. Kind of difficult to see on the paper. I was working this one out earlier. They want to know the measures of angle A and B, which, if you look at them, and you know what I always say, you know what they always say. If you look at them, angles A and B, so A's down there, B's over there, those are in the same relative spot. They're going to have the same measure. Okay. So if we think about them, we don't know what they are. We'll go ahead and call it X, and we'll call that one X. And we're dealing with an equilateral triangle, which is also going to be equiangular. So every angle that's unknown in there is going to be X, isn't it? So that's kind of interesting. So angle A and angle B are going to be the same. The measure of angle A is going to equal the measure of angle B. And we're going to have to find that, and we will. In order to find that, we could realize that, if we look at angle A, it's this one here. We would know that X plus X plus X is going to equal 180. So 3X is going to be 180. So X is going to be 180 divided by 3, or 60. So the interior angle measures in an equiangular or equilateral triangle, for that matter, always measure out at 60 degrees. 60 degrees. So then we're asked about this angle ADC. Angle ADC is this larger angle. It's kind of hard to see on the drawing. I'll use my yellow highlighter. It's this larger angle here, which is comprised of two x's. Okay, so you could use that reasoning to say, to find that, or you could say that the measure of angle ADC is the measure of two smaller angles. We could say it's the measure of angle ADE plus the measure of angle EDC. And ADE measures out to be 60, and EDC also measures out to be 60, and that sum then is going to be 120. And we knew that all along because we could have just doubled the 60, right? So anyway, that ends up being 120. Okay, so our two answers for this one, the measure of angle A, which equals the measure of angle B, is 60, and the measure of angle ADC is 120. All right. So, guess we'll go ahead and move on to the next one. If we're ready for that. Before we do, maybe we're ready for this. Did you hear about the mathematician who's afraid of negative numbers? He will stop at nothing to avoid them. He will stop at nothing to avoid them. I don't know if you get that one or not. Negative numbers. He will stop at nothing to avoid them. Anyway, that was really bad. Really bad. Got it. Number 3 says, suppose that the triangles of problem 3 are isosceles, where ADE and DEC and ECB are the vertex angles. Okay, so what I'm going to just do is kind of recopy this, and you'll probably need to do this as well. So that's going to be that drawing. It's kind of like a parallelogram. So it's going to look like this. 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 So that was ADCB, ADCB. with E down here. Okay, so they're saying that DEC is a vertex angle. So this is going to go like this, and this is going to go like this, and ADE. So this is a vertex angle. DEC is a vertex angle, and ECB. Those are the vertex angles. So that means that this is congruent to this, which is what? So that's an isosceles triangle. So that's congruent to that, and that's congruent to that. Well, that's good to know. And it also means that all these base angles here and here and here and here are going to be congruent. Right? And I guess these are going to be congruent too. So all those things are congruent. Cool. So if the vertex angles each have a measure of 58, so let's plug that in. The vertex angle has a measure of 58. That's 58. That's 58. What's the measure of angle A? Ooh, so we know A. We know that this one here and this one are the same. So we'll call that x and x. So we know that x plus 58 has to equal 180. So 2x will equal 180 minus 58. So that's 122. And x will be 122 divided by 2. That's going to be what? 61. So the measure of angle A is 61 then. So let's plug those in. So that's 61 down there. That's 61. That's 61. That's 61. That's 61. And that's 61. So then they say, what's the measure of angle? The measure of angle BCD. BCD is that larger angle there. So the measure of angle BCD would be the 58 and the 61 summed, and that's going to end in a 9, and it's, I guess, 11 degrees. 11 degrees. And the measure of angle A was 61 degrees. Cool beans. Whoomp. There it is. All right. So that gets us through that. Let's see what else they got for us. Wow, just about done. Lesson check. Do you know? Okay. Measure of angle A. Huh. Oh my gosh, really? The base angles are congruent. The measure of angle A is 70. That's easy. The measure of angle A. Base angles are congruent. The measure of angle A is 53. That's easy. The value of x. That's a little trickier. We know that x and this other thing are going to be congruent. So we know that x plus that 30 have to sum up to be 180. Have to sum up to equal 180. So 2x would be 180 minus 30, or 150. So x is going to be half of 150, or 75 degrees. Number B, this one's kind of like that one where we couldn't tell where the 54 went, but we can see that NO bisects LNM, which means that LNO is perpendicular to LM, which means that's a right angle and that's a right angle. So then that 42, I guess, is the base angle, so that's 42, so we would know that 42 plus x plus a right angle have to sum up to be 180. And so I guess if we do that kind of thing, we would know that x is going to be 90 minus 42. So that's going to be something 8. Is that 38? 48? Is that 48? 48. Okay. So that ends up being 48. So I think that this is probably going to be a pretty relatively simple set of homework for you to do. Got one more to look at, I think, and then that's it. And then that's it. Good. So the measure of one base angle of an isosceles triangle. So you got to be able to draw these things. You got to be able to sketch these things. They don't have to be perfect. And keep in mind that they don't always have to be oriented that way either. I could orient these things maybe. Oh man, I could orient something like this, like that. Okay. So maybe these are congruent and these are the base angles. So the measure of one base angle is 23. So I know this is 23. And they're telling me it's an isosceles. So I know the other base angle. I know that the other base angle is 23. All right. So it says, what are the measures of the other two angles? Well, 23 is one of them. 23 and So we got to figure out the other one, that one. So 23 plus 23 plus x would be 180. So 46 plus x would be 180. So x would be 180, take away 46. And I guess that's going to be 100, something that ends in a 4. Is that 134 degrees? So 23 degrees and 134 degrees. There you go. Cool beans. So that's chapter 4, section 5. Isosceles triangles, equilateral and equiangular triangles. I would tell you another lame joke, but you probably aren't ready for it. Did you hear the one about the statistician? Probably. It's been real. It's been fun. I hope you have the best Wednesday of your lives. See you.
Good. Good.